Okay, welcome back. And what we are going to do now is look at the method of Lagrange multipliers. Specifically to solve problem which are constraint optimization problems with a equality constraint, right? So, which are of the form minimize over x, f of x, such that g of x equals 0. We saw earlier that to solve this problem, um, a necessary condition that optimal solution should satisfy is that, of course, g of x star should be 0, and secondly, we also argued that del of f of x star should be minus lambda times del of g of x star for some lambda, right. So, no sign constraint. It can be either positive or negative. This has to be satisfied. Now, let us see how we can use this insight that the gradients have to align either in parallel or anti-parallel for x star to be some optimal point to actually solve a simple problem, right. So, we will take a simple example and try to solve this using the method of Lagrange multipliers. Okay, so let us take a example where we have a function example. This is a function of two variables, let us say x1 and x2, and the function looks like this, right. So, x1 squared plus 2x2 plus 4, let us say x2 squared. This is just a quadratic function, a simple quadratic function, and now we want to argue that we somehow want to also, of course, I need to also say what is the g. Let us say g of x1 comma x2 is x1 squared plus x2 squared, let us say minus 1, right. So, which means that we want to find an x1 x2 which is on the unit circle, such that because g of x1 x2 should be 0, which means that x1 squared plus x2 squared equals 1, which let us say minimizes x1 squared plus 2x2 plus 4x2, right. So, this is the problem that we want to solve. Now, how do we solve this, right? Well, our Lagrange multiplier insight tells us that a necessary condition is that del f of x star should be minus lambda del g of x star. Now, how can we exploit this condition? Well, let us try to compute for any x what is del f of x and del g of x, right. So, in this for this particular specific problem that we have at hand, right. So, for any x del f of some x1 x2 would be what? In this case, it is simply the partial derivative with respect to x1 in the first component and partial derivative with respect to x2 in the second component, which would happen to be, let us say, 2x1 and 2 plus 8x2. This would be the gradient with respect to x1 x2 at any point x1 x2. Similarly, the gradient with respect to the constraint function g at x1 x2 is going to be something like, maybe in this case it will be 2x1 2x2. Good. Now, we know by the method of Lagrange multipliers that the optimal should necessarily satisfy something, which is equation 2, which means that that gives us some set of equations here, right. So, what equations does it give us? It gives us that 2x1, which was the gradient of f, and 2 plus 8x2. Now, this should be minus lambda times 2x1 2x2, which is del g. Let me just note it down so that we are clear what we are talking about. This is del f of x1 x2. Okay, maybe I should at x1 x2, and this is del g at x1 x2. Good. Now, this simply says that we have a system of equations, right. So, what is the equation? So 2x1 should be minus lambda times 2x1, that's equation number 1, and 2 plus 8x2 equals minus lambda times 2x2, that's equation number 2. Okay, so let's look at equation number 1. 1 implies 2x1 plus lambda times 2x1 equals 0, which implies 2x1 into 1 plus lambda equals 0. Right, so this should necessarily happen. There are two ways this could happen, right? The first way is, so this implies either x1 is 0, for which this might be true, or lambda equals minus 1, when in which case also this is true, right? Well, let's maybe first look at the case 1 when lambda equals minus 1, right? So let's assume lambda is minus 1. If lambda is minus 1, then how can we exploit the fact that if lambda is minus 1, what can we say? We can say, now we can look at equation 2 and say that 2 plus 8x2 should be equal to minus of lambda, which is minus 1, times 2x2, which implies 2 plus 8x2 now equals 2x2, which further implies minus 6x2 equals 2. Now that gives us a value for x2 as minus 1 by 3, right. So if we know that lambda is minus 1, which is case 1 that we are looking at, then x2 necessarily has to be minus 1 by 3. But how do we get x1, right? So if I know x2, then I can simply get x1, because we necessarily have to satisfy not just the Lagrange equation, but also the feasibility equation, which is x1 squared plus x2 squared should be equal to 1. This also has to be satisfied. Now we have found x2, now from which we can simply get x1, right. So x1 squared then would be 1 minus x2 squared, which in this case is 1 over 9, which means that x1 squared is 8 over 9, which means x1 is either plus square root of 8 by 3 or minus square root of 8 by 3, right. So there are two options for x1. Okay, so case 1 when lambda equals minus 1 gives us two possible, potential solutions, which are as follows. We found x2 as minus 1 by 3 and x1 as either square root of 8 by 3 or minus square root of 8 by 3, right. So which implies the points that are important here are, well, x1, x2, which means that it is square root of 8 by 3 minus 1 by 3, comma, minus square root of 8 by 3, comma, minus 1 by 3. We have two sets of points, set of 2 points. So this is, remember, case when we argued that lambda is minus 1. The other case is, it could so happen that x1 was 0. Right. So there are two cases that we got from the first equation. 2x1 times 1 plus lambda is 0 was the equation, and that can either be satisfied if x1 is 0 or if lambda is minus 1. We have already looked at the case where lambda is minus 1. Now if x1 is 0, now how do I get x2? Well, now we look at the feasibility equation, right. So the feasibility equation would say x1 squared plus x2 squared equals 1, which implies if x1 is 1, then x2 squared has to be 1, which means x2 equals 1 or minus 1. Now this then tells us the set of points which are important here are the following, which would be x1 is 0 and x2 is 1, and x1 is 0 and x2 is minus 1. So now we are saying that if it is optimal, then necessarily it has to satisfy a certain equation, which means that there are only 4 possible options for the optimal point, right. So now to find the optimal point, right, so to find min over x f of x such that g of x is 0, in this case, right, what we have done is substitute each potential solution into f, right. So, you have 4 possibilities, correct, and now we substitute each of these possibilities into f and see which one gives us the least value. Now, let us go ahead and do that for completion's purpose. So, what was our f of x? Our f of x, remember, was, let me go back to make sure I have the right f of x, x1 squared plus 2x2 plus 4x2 squared. Right. Now, what does this tell us? This tells us that if f of, well, let us do the simple things first, 0 1, f of 0 1 is what? It is simply 2 plus 4, which is 6, and f of 0 minus 1 is again 2, well, not, so it will be minus 2 plus 4, which is 2. These are the two values. Now, what about f of square root of 8 by 3 comma minus 1 by 3? Well, that is going to be 8 by 9 minus 2 by 6, 2x2, x2 is minus 1 by 3, plus 4 times x2 squared, which is 4 over 9, right. So, which is 12 over 9 minus 1 over 3, which is 4 by 3, which is, let me make sure I am doing this correct, 4 over 3 minus 1 by 3, I think this is 1 if I am not wrong, yeah. I think I am right. Oh, sorry, okay, I think it is not 6, it is 3, right. So, that would give me 4 by 3 minus 2 by 3, which will be 2 over 3. So, that would be the third value, and the other one that is left is minus square root of 8 by 3 minus 1 by 3. Well, x1 is anyway getting squared, so that will also be 2 by 3, right. So, in fact, we have 4 values, and the theory of Lagrange multipliers can be used to say that your function constrained by g of x is equal to 0 will attain the minimum at the point where one of these potential solutions is the smallest. In this case, it so happens that these 2 points have the smaller value, which is 2 by 3, right. So, if you compare 6 to 2 by 3 and 2 by 3, 2 by 3 is the smaller one. So, and that is achieved at 2 points, and both these points happen to be points where the function attains its minimum value in given the constraint set. And the point where you have the highest value, in this case 6, happens to be the point where you can show that this is the point where the function will attain its maximum value also, right. So, which means that these two are minimizers, and in this case this guy happens to be the maximizer, right, and this happens to be what is called as a saddle point. So, this is neither a minimizer nor a maximizer for this function, right. So, but let us leave that aside, right. So, the idea was, so let me summarize what we did in terms of the method of Lagrange multipliers. What we did was the following. We started by saying that if x star is an optimal solution, then it necessarily must be the case that the Lagrange equation is satisfied and the constraint is satisfied, and we converted that by looking at the gradients into a set of equations. And by carefully analyzing these equations, what we did was we kind of solved for lambda and used that to solve for x1 and x2, right. So, and that gave us in this case 4 possibilities, and by plugging in each of these possibilities into the function, we saw that some of these points actually gave the smaller values and some of these points gave larger values. And the points which give the minimum values are indeed the minimizers of this function, and the points that give the higher values are actually end up being the maximizers of this function. So, this in general is the method of Lagrange multipliers, where you can directly solve this problem without really moving in any direction or doing any iterative process or anything of that sort. So, this is a very good method when you can actually solve for lambda and the equations, right. So, the next question that brings us to the next question, that like in general, is it possible to solve the system of equations that Lagrange that satisfy the Lagrange equations? Well, in general this may not be true, right. So, may not be true, right. So, it is not always possible to solve your problem analytically like how we did for this simple example. This is a nice example to illustrate the power of Lagrange multipliers, but in general it may not be true. So, now what else can we do when we do not have an easy way to solve using the method of Lagrange multipliers? Can we do something else like kind of like gradient descent, which will iteratively get us to the optimal solution? There are several possible ways of attacking this problem. What I want to do today is give you a method for now, and then we will talk more about when this method would actually perform well. Under what conditions can we argue that the method or the algorithm that I am going to give now will actually get you the optimal solution, right. So, the method of Lagrange multipliers is very powerful, but then it needs careful solving of equations and so on, but then we still want a method that will automatically get us to the optimal. And gradient descent was one such method, but then it worked only for unconstrained optimization problems. Can we do something for constrained optimization problem? Maybe we will have to sacrifice something with respect to the type of functions for which the method will work. Nevertheless, is there a method that will work for a general constrained optimization problem? The answer is yes and no, and I am going to put down the method and then we will talk about when this method will actually work a little later. The method is remarkably similar to the gradient descent algorithm. In fact, it is what is called as a projected gradient descent algorithm. So, what is the projected gradient descent algorithm? What does this algorithm do? Well, let us remind ourselves what was gradient descent doing. So, you start with some x naught, right. So, initialization, and then for t equals 1 dot dot dot, maybe there is upper bound depending on how many number of iterations you want to run this algorithm for. Then you say that xt plus 1 equals xt minus eta times del f of xt, gradient at xt. This was our simple gradient descent algorithm. Now, what was the problem with this algorithm? The problem with this algorithm is this xt plus 1, this update, when I am in some xt, if I move, let us say this is my negative del f of xt direction. If I move along this direction, it might so happen that if I take a step size and if I move here, my constraint set could be something like this, right. So, this is the set of points where g of x is, let us say, less than or equal to 0, for instance. Now, I am at some xt, my function actually grows in this particular direction. If I move in this direction, I might potentially take a step that will take me out of the feasibility set. Now, it's very hard to tune step sizes to always remain within the feasibility set, because that is a property that will intimately depend on the property of the feasibility set and so on. On the other hand, what we could potentially do is, we will assume that, okay, so I am at some point, I will take a gradient step, I might potentially go out of the gradient, out of the feasible region. What I am going to do now is, after taking this gradient step, I will basically come back to my feasible set by projecting the point where I end up after taking the gradient step onto the feasible set, right. So, this point, let us call this is my xt minus eta del f of xt, and now this point is going to be the projection of xt minus del f of xt onto feasible set, right. So, we will call this projection. So, what is a projection? A projection is a function basically, so which takes, let us call that function pi, right. So, it takes any vector x, and then it finds the minimum y such that the length squared is as small as possible. But what is the what should y satisfy? It can't be any y. The y should belong to some set S. Now, what is the set S? We will say the set S is simply our constraint set, which is the set g of x is less than or equal to 0. Right? Set of all, or rather let me say y, set of all y such that g of y is less than or equal to 0. Right? So, basically, from the red point, which you end up outside the feasible set, you find the closest point in the feasible set and move to that point. And the operator that does that is what we will call as a projection operator. So, this is a projection operator. So, all we are doing is that we are taking a gradient step. Well, that might potentially push us outside the constraint region. So, we want to come back into the constraint region, and what would be the best way to come back? Find that point which is closest in the constraint region and come there, right. So, so the only modification of gradient descent to projected gradient descent is that we have this projection operator, right. So, this is the gradient step and this is the projection step. Now, this is an iterative algorithm, right. So, this is very much like our gradient descent algorithm, just that we are doing this extra projection step. The question is, this seems very simple, but then what is the catch, right. So, the catch is that there are a couple of things that one should be very aware of here. One is, this depends on the fact that you can in fact do your projection onto your constraint set efficiently, right. So, that is the first important thing. So, if your constraint set is really messy, right, so it is really complicated, then doing this projection might not be that easy, right. So, but if you do have a constraint set which is nice, where you can efficiently implement this projection operator. When I say efficiently, it means that, let us say it's polynomial in the dimension of x, let us say. I mean, if it's even, let us say if it is not polynomial, let us say maybe if it is faster than that, it's even better, but then you want at least polynomial time efficiency for implementing this projection operation. If that is possible for your constraint set, then this algorithm can be run. Now, the question is there anything else that we should be aware of for guaranteeing that as I keep doing this, I would indeed converge to the optimal solution, right. So, I want to finally converge to a point where in the constraint set which minimizes my function. Of course, I will be within my constraint set because by definition I am doing this projection onto the constraint set, because which means that every iterate that I have, I will be inside my constraint set. But the question is, eventually as I keep doing this, will I eventually reach the indeed the optimal point or not? That is what we should be worried about. And one can show, and we will talk more about this in the next class, in the next video. We'll actually show that if your constraint set satisfies something nice, specifically if your constraint set is a convex set, right? So, and we briefly talked about convexity earlier also, right? So, convex constraint sets, and so which means that it's in some sense, think of it as a nice set. We'll define this formally next time because it becomes important to understand convexity from a machine learning point of view. You'll talk more about convex sets in the next as we go along. But then let me briefly tell you that if your constraint set is nice in the sense that it is convex, then we can argue that this algorithm will in fact give you the optimal answer. And if your function that you are optimizing is also convex and has some nice property, we can also argue how fast you will converge to the optimal. Probably we will not do that in this set of lectures, but what I also want you to understand is that the goodness of the algorithm also comes with respect to the function that you are trying to optimize and the set in which your constraint is in, right? So, as long as the set is convex, this algorithm will do well, and if your function has more nice properties, some of which we will talk next time, this algorithm will do even better, right? So, in the even better meaning that of course you will reach only the optimal point, right? So, there is nothing more with respect to the point that you will reach that you can do better, but then you will do better in terms of how fast you will reach that point, right? So, that can be argued in this case. So, this is the projected gradient descent algorithm, and we will talk a bit about this in the next coming lectures. And we'll for now I want to summarize by saying that so far we have looked at the problem of optimization in general. We have talked about gradient descent which works for unconstrained optimization problems. We looked at the constraint case and we came up with this method of Lagrange multipliers. We saw an example where you can in fact analytically solve certain problems using the method of Lagrange multipliers. In some cases you may not be able to solve it, and so we want like a general purpose algorithm, an iterative algorithm, and it turns out that when you have nice functions and nice constraint sets, the projected gradient descent algorithm works wonders. And we will see in a lot of machine learning applications, your functions are typically nice, your sets are typically nice. When I say nice, it means that they are convex, and so these projected gradient type algorithms typically tend to work well. We'll talk more about convexity and how it is related to machine learning in the coming classes. Thank you.